Okay, cool. There we go. Yeah, so hello. I wanted to first talk about some stuff that I saw in Hacker News this morning. This hard drive here, it was pretty cool. I don't think it has the number on here, but it was like 60 terabytes of data, and the part that I saw there was kind of interesting was 12 gigabytes per second of sequential reads. And that's very exciting, and I'm going to come back to why that may be interesting a little later in the talk here. Another thing that when I saw that I was reminded, does anyone remember Fusion IO? Does Fusion IO sound familiar? Okay, like 2 people maybe, 3 people. Okay, do you know who the guy is up in the corner? Like raise your hand, do you know who that is? Yeah, Steve Wozniak, the Apple guy. Yeah, in 2010 he started a company called, or he was co-founder or something. He started a company called Fusion IO, and they were building really cool storage technology. And then that reminded me of this thing that I read recently, Dropbox. I think in it might be on there. Yeah, 2022, Dropbox had this article where they talked about how they were migrating away from SSDs and onto hard drives, which I thought was just like a very fascinating thing. And in particular, like maybe you've been sleeping on hard drives, but there's been some recent developments in like the spinning metal area of databases, which is shingled hard drives. And that was like a thing that was entirely new to me. And you can see there, like if you Google actually Dropbox SSD SMR hard drive, you'll find this great article that talks about all the reasons why they went away from SSDs and back to hard drives. And it's just a very fascinating article. Okay, so I've only got 25 minutes, and I was thinking like, boy, there's like a lot of stuff that I'd like to talk about when it comes to Ethereum indexing. And so my first thought was like, well, I can hit these 25 topics and maybe do, you know, 1 topic a minute. But then I was like, man, but that really doesn't like cover all the stuff that I would be excited to talk about. And so I was like, well, there's really like 50 things that we could like explore. And that gives us like 30 seconds per topic. But then I realized like this is just a terrible approach. And so I willed it down to 3, which gives us about 8.333 repeating, of course, minutes per topic, which I think is much more reasonable. The way that I'm going to break this down is I'm going to share kind of how I think about software dependencies in general, and then we'll kind of like also explore like I think some unique characteristics of the Ethereum data space as it relates to dependencies. And then I'm going to talk about like this pattern. I've built like a lot of indexers over the years. I've been in this space for a long time, and there's been like a couple things that I've seen like kind of just like I've done some things like over and over again, and I've kind of distilled it down to a pattern. And so I'm going to share that with you today, and maybe you know, inspire you to build your own indexer, and perhaps you could use some of the ideas in this pattern. And then finally, I love databases. I really enjoy Postgres. I like other databases as well, but Postgres is in particular a thing that I enjoy. And so I'm going to share some fun Postgres tips. And so let's see. Yeah, let's get started. Oh yes. Okay. So I have a project called Index Supply. It's a company that sells indexing stuff. But today, like, I'm going to convince you to not buy my software. Even though I do this stuff, I actually think it's like great fun to build it yourself. And I also think that there are particular situations in which it actually makes sense for you to build it if you're working on a company. And we're going to explore that here in just a second. So I'm not being facetious. I'm giving this the college try, convincing you to build your own indexer. Do not use my stuff. Okay, so let's get into kind of how I think about dependencies. So to start, like I want to talk about Ethereum in particular, and so like there's kind of like this base question of like what is, you know, indexing Ethereum, and so quick poll here. Who's read the yellow paper? That's about like I want to say like a third of the audience. Okay, great. So
in the yellow paper, you basically get, and like the way that I'm kind of like thinking about this is that when you think about dependencies, you have to pick some anchor point, right? Like at a certain point, you're going to say like, okay, I'm going to go like invent a new kind of hard drive technology. Like, no, you're not going to do that. You're going to buy a hard drive, and then you're probably going to like use a file system. You're probably going to use an operating system. And so like there are these things that we kind of like anchor around, and then like on top of those anchors, then we start to think about like, okay, should I build it? Should I buy it? And so I think in particular for Ethereum, like we have like these primitive data structures that are built into execution clients, and they give us things like blocks and transactions and logs. But the databases that are within these execution clients are really optimized for processing the transactions, like not necessarily optimized for arbitrary queries. And I think that's like a fine thing, and perhaps there's like opportunities to blend those two types of workloads together, maybe. But we can kind of, I think it's fine actually. Like in particular, Geth has like these freezer files. Has anyone worked with a freezer file? Raise your hand. No one has worked with a freezer file. I don't see anyone who's worked with a freezer file. Okay, these are really cool. In Geth, like all of the transaction and log data is just like packed into a binary file on this file system. You can read through it very quickly. It's very interesting. If you just Google freezer files, you'll see some interesting stuff come up. Okay, I'm going to keep going here. Okay, so one of the interesting things about the Ethereum landscape is that we have these core primitives, we have the nodes, and we have a standard JSON RPC API. And what's really great about this is that if you build with that as your dependency, you have this really nice commoditization effect where if you don't like your particular provider, they're not doing it for you, you can go to like 10 other providers, and so you really do not have hardly any vendor lock-in. Now there's some disadvantages, like if you just work at this level, because you have to actually develop software, you have to manage databases, so there's a little bit of a cost to it. And so, if we kind of move up, if we go to like the other end of the stack, and you use something like, like what I build, or there's like a handful of other products out there that give you like a more robust API to access the Ethereum data, and maybe you don't have to use a database, but now you're like entirely dependent upon that API. And if that API doesn't work for you, you've probably built your application around its abstractions. And so, you want me to move over? Okay, I got a subtle hint that I should move over. You want me to keep going? Okay, perfect. Is this better? Wonderful. If you build around those types of abstractions, you can kind of hamstring yourself eventually if it doesn't end up working out for you. And so, like another way that I like to look at this is when it comes to like dependencies in general, like let's say that you have like a very high value project. Like you could have a high value project or a low value project, right? Something you're just messing around on the weekend, or you could have something that you're trying to build a business on top of. And within that category, you have like low skills or high skills. And if you don't know anything about about interacting with databases or keeping data around and easily accessible, then you might want to buy something, and that's fine. But I think one of the things that I would like to kind of posit today is that indexing Ethereum, like, it actually isn't that hard, I don't think, and I'll throw like a couple things kind of at you to kind of encourage you to, like, if you happen to be in this category of you're working on a high value project but maybe your skills aren't there, I think that there's absolutely stuff that you can do to advance your skills so that you can build something that you're really proud of. And then on the other end of the spectrum, it's like, okay, you've got a high value project, you have high skills, and here, I think it's like very important to build it, actually. And if it matches the core competency of the company or the project that you're working on. And I think the most important thing here is that, like, when it comes to thinking about dependencies, it's like you don't want to outsource your thinking. You want to kind of come up with your own opinion and like your own motivation for why you're doing a particular thing with your data. And when you build it, you're forced to think about it, and you're forced to lay something out that you think is going to match what the business needs. Okay, so you got a low value project and you have low skills. I say just jam it together. You do whatever. Find the quickest path to get the thing online, and that's fine. If you've got a low-value project but you have high skills, I think actually kind of both can work. And the way that I kind of think about this is, if you form an opinion of how you, you're working in a particular problem landscape, and you come up with your own opinion for how you want to build a solution, and then you maybe do some shopping. You say oh wow, there's a couple projects that already exist that are doing the thing that I would do. And so in this particular case, you're not outsourcing your thinking, you're outsourcing the maintenance of that software, which is a real advantage. And so even if you have the skills, it really is a toss-up in terms of whether you build versus buy. Okay, so part 2. I'm going to go over this essential indexing pattern. And like I said, I've used this for probably, 5 or 6 years. I've worked on some pretty big websites in the Ethereum space. And this is the pattern that really has worked well for me. So I'm going to share it with you today. And it's basically, there is this old Fred Brooks quote that says, show me your flowcharts and I'll continue to be mystified. Show me your tables and I won't need your flowcharts. And so I like to start with the tables first. And so the building block here is that you have a table called blocks, and you keep track of the number and the hash of the block. And then you have all these auxiliary tables like foo, which is your indexed data. And within your indexed data, you have a block num, you have a reference to a block that you've inserted, and then you have this column bar, which represents just some arbitrary data that you want to index. Okay, so now here's a wall of code, but basically this is the core function, and I won't go into every painstaking detail here, but this is the core function that uses those two tables to effectively index data on Ethereum. And it uses some, you can kind of see here, there's some RPC code going on, there's some database code going on. In particular, this thing down here at the bottom, this copy logs, that's a really cool Postgres technique that allows you to really quickly load data into a table. And so again, I'm not going to go through the whole detail here, but I wanted to show you this because it's actually, I'm saying this can get you very, very far. And in fact, you can even just kind of copy and paste this into a project to kind of help bootstrap you and get you started. At some point, I might even throw this on a gist or something, so that someone could copy and paste this, and we'll make it work and compile and stuff. Because right now it doesn't, but it's more or less there. Okay, so another thing with pointing out is that the current kind of high-level architecture of Ethereum indexers kind of fits into this first category. And so basically, like I said earlier, we have these sources of data like an RPC API or an execution client, but they don't really give us the type of interface that we would want when it comes to building queries for our applications. And so what we do is we read the data from the source. It's like an ETL workload, right? We extract the data from the source, we transform it, and then we stick it in another database that gives us flexible queries so that we can build stuff onto our apps. It's fine patterns like what the graph uses. It's a very common pattern in the space. I think that there's another pattern though down here at the bottom which I'm more interested in, which is how can we just continue pushing our query logic onto the source data, and instead of having ETL, we just have query to the database. And I think that's a whole interesting path to explore, and I've got some ideas there and would be happy to talk about it, but I just want to kind of call that out. Okay, so part 3, we're coming in here on the end. I'm going to go into some Postgres tricks. And then another poll for the audience here. Who uses Postgres? Okay, wow, quite a bit of people. This is by far the biggest, positive affirmation of a poll that we've done so far. It was about I would say 70%, maybe 75%. Okay, great. So you've got the essential indexing pattern, you've got the architecture. What are some here's a quick checklist of really good features to use when it comes to indexing Ethereum. First one is copy. Show of hands here. Who uses copy? Okay, a few, let's say 10 to 20%. Okay, so if you are inserting more than, let's say, 3 rows at a time, and you're using insert, you are wasting compute cycles. It is massively inefficient. There is almost practically zero downside to using copy. So if there's one thing that you walk away with today, and you're a Postgres user, and if you're ever inserting more than, let's say, 3 rows, like move over to the binary copy and you will instantly see a major performance boost. Advisory locks, another really cool feature in Postgres. So it's an in-memory lock that you can use, so it's very cheap. You can have thousands of them, maybe even hundreds of thousands of them. And this is a really nice way if you want to build an indexer and you want to have 2 of them and you want to perhaps like run them in an HA configuration, but you only want to have one doing the work at a time. An advisory lock is a great feature to use. Another feature that I like is table partitioning. And so we'll kind of explore this a little bit in my next tip. But basically, you can take like a table and you can specify a partition key on that table, and then you can specify how many partitions you want to run, like let's say 10, and Postgres will automatically create 10 child tables for you, and then when you query the logical table, it'll automatically find the right partition table to get the data from. And this is like completely opaque. You don't have to do any of this stuff in your application. And it gives you a really nice performance boost when you are bounded by disk I/O. And so let me kind of show you how to kind of think about like when you may be disk I/O bound. To do that, I'll quickly introduce a Brin index. Show of hands, who knows about a Brin index? Even fewer. This might be the smallest number, but I see you out there, and bless you, because this is a very fantastic index for some use cases. So basically, like when you have a table and you put data in that table, Postgres will put, like if you insert a row into a table, Postgres will take that row and it'll end up in a file on the file system. Postgres, by default, uses 8 kilobyte file sizes, so that means that it's going to be spreading your rows across multiple files on your file system. What a Brin index will do is it will basically, if you have a column that has a high correlation, like so for example in Ethereum, block number would be a high correlation to the way that your data was going to be laid out on disk if you do an insert only append kind of write style. So if you're just like keeping up with the blockchain and you're writing data and you're putting the block number in those rows, then like as you store stuff on disk, it's going to correlate with the block number, right? And so this is a great use case for a Brin index because what you do is you have this super tiny index, much smaller than a B tree, and it keeps like, we have like this page block up here that says, okay, in this page block 0, I have block number 0 to 99,000, and those rows are stored in pages 0 and 1. And so you basically have like this top level, like higher level index that like, you know, for a given block number, it can basically redirect you to the right set of pages to read in the operating system. And so let me quickly show, we've got about 2 minutes left. Let me quickly show you, so here's an example. So I have this table called logs. You can see I got a block num column there. This table's about 4 gigs. And then you can see I checked the correlation of the block number. It said 83%. This is like another like, you know, ancillary database thing. I know it's 99%, and I queried it like earlier this morning and it was saying 99%, and then all of a sudden it just stopped saying 99% and started saying 83%, and so then I became very angry. But that is what it is. I think it's wrong, but that is, I'd like to find that stuff out later. Okay, so here's another cool Postgres tip. If you're writing queries, you've got to figure out like the explain command. It's like it is literally life-saving. Like get to know this command, and you will become a great database administrator. So you can see here we hit a bunch of blocks, about 500,000 buffers. So multiply that by 8 kilobytes. That's how much data that we read. You see, I created the Brin index. And you can see that index size is only 320 kilobytes. And I had a 4 gigabyte table, so a very small index. And then the resulting query after that is I only had to read about 42,000 buffers. So like a massive decrease in the amount of I/O that was going to happen there. I'm just going to go ahead and show you what a B tree index would do, which is like your default index. So you can see here, it's a much bigger, you know, we went from 320 kilobytes. B tree index is 250 megabytes, much bigger index. But you can see down here, it's just, you know, game over. B-tree index is really great. You know, much faster, much fewer buffers. But sometimes you don't need to have that level of performance, and you might want to trade off storage size. Also, it's very quick. Like if I have a terabyte table and I create a B-tree index over a block num, it's actually going to take a long time because it's going to seek scan that whole table. a Brin index will happen much faster. So even if you're in a pinch and you're just trying to like find some data in a big table and you don't want to wait to create a B tree, creating a Brin might actually be a good stopgap. Another Postgres little bit of tidbit of knowledge is that you have a B tree index and that is going to have a ton of data in it, and you might say like when you're doing a query and you have a huge table and you have a huge index, does Postgres have to load the entire index into memory to be able to do the search of the B tree, to be able to find the right rows to return to you? The answer to that question is no, and I thought this is kind of like a fun fact, but in the docs it says, typically when you have a B tree index, so if you have an index that's, let's say you had a table that's a terabyte, you got an index that's like 100 gigs, 99% of that is going to be the leaves, which means that when you want to go search that table, before like you need to find like the target rows, you're actually going to be able to keep that index in memory because the majority of the data that you're going to be searching on is going to be very small. Okay, so time is about up. So I didn't. Oh man, I'm really bummed. I really wanted to talk about CTIDs. And I didn't, but it's really cool because whenever you query, I'll just briefly mention it, whenever you query a table, you can always ask for a CTID. It's a hidden column on a row, and it tells you what page and what offset into the page that particular row is in. And then there's some cool things that you can do with clustering if you want to rearrange rows as they sit on disk for improved I/O performance, you can do that with cluster, although it's not an online tool, you would have to recluster if you wanted to change it. Okay, whirlwind tour there, but that's it. I wanted to kind of plug Farcaster. We have a Postgres channel, and I encourage you, if you're interested in any of this stuff, check out the Postgres channel. There's a lot of good discussion happening on there. So thank you very much.
Thank you, Ryan. Question time. So the audience have some questions for you, and we're going to go through it. The most highest
reorgs.
Yes.
So that code that I showed earlier handles reorgs. It was in there, and so maybe you got a photo of it, or maybe we can I can post it on Gist or whatever. But there are very easy ways to handle reorgs. It's not that big of a deal. Don't let it scare you. We can definitely solve that problem.
So first question, one PTA. One picture for us was handling blah, blah, blah. So 5 votes. It means that's the most important question now on the stage. So can you answer that one first?
Yeah, we just did that one. So I think the next one would be how to deal with load balance RPCs. Yeah. So it's kind of also kind of a pain in the ass. Basically, you send a request to an API. You say, give me the latest block. And it's like, the latest block is 10. And then you say, OK, great. Now give me all the logs for block 10. But it's load balance, so it goes to a different node. And the awful thing, the sin of the JSON RPC API is that if you ask for logs and you give it a block number that is higher than the block that it's currently processed, you would think it would say, hey, I don't have that block. I don't have these logs. The error. It does not do that. In fact, it'll just give you no data back, as if it had that block but did not have those logs. And so this is a big gotcha, and you really have to look out for this. There are a couple tricks. I'll just go ahead and give you one now, but it's like 50% success rate. I don't think there's a 100% way to deal with this, but one hack is the JSON RPC API allows you to send batch requests, and sometimes there are proxies that will take batch requests and split them up and give them to different nodes. But assuming your API provider doesn't do that, and it just takes the batch of requests and sends them to one machine, you could hack this by putting your get logs request with a get block number request, because if you ask for a block number by a specific number and that block number isn't on that node, it will return an error. So this is like one way to trick the node into giving you an error when you ask for logs and you don't have the block. So there's a couple other solutions, I think, but we'll keep cruising here.
Yeah.
Do you think it makes sense to have an indexer interoperability? I don't know about number one, that first question. I'm going to go on. So what do you think about using ClickHouse or times? Oh, that's interesting. Yeah. So I mean, here's the deal. If you want to do like a group by, or you want to do like a count or a sum over like 1 million rows, or over 1 million rows. Like if you want one column over a lot of rows, you might want a columnar database. And the idea there is that you are wanting to reduce, like, so instead of like, if you don't have a columnar database and you have to like get the value out of a row, that means that you have to go scan a whole bunch of operating system table pages to get all of the rows, but really you only care about one, and so, you know, for doing like an aggregate or something. So that's a lot of wasted I/O, right? And so the idea is, can we do better? And so for very specific use cases, when you want to do aggregated stuff, a columnar database might save you from a lot of that I/O. So, you know, it is a way to improve performance if what you're trying to do is like more analytical queries that you know, works on aggregated data. So not great for OLTP stuff, but yeah, if you have aggregates, it's fine.
One more minute to go.
Let's see. Do you think it makes sense to have an index? Oh, I already did that one. I didn't have an answer there. Can you explain better why a Brent index is so much smaller than a B tree? Yeah, because a B tree is going to have like some knowledge of every row in the table, right? Like every row in the table is going to have some map onto the index structure, whereas a Brin is like lossy, right? So in a Brin index, I have one node in the index, but that one node in the index can actually cover, let's say, 100,000 rows, right? It can say, hey, you know, you're querying for block number 10, and the Brin index says, okay, well, I know that block number 10 is like in this block of operating system pages. And so then you have to then go like basically sequential scan within that set of pages, but at least you're not scanning on the entire table, right? So it's like the Brin index is smaller because it just simply has less information, but it can cut, you know, if you're just trying to get rid of a